Thank you, Niels. So with me today, I have David Meyer and Dino Farinacci, if I didn't butcher that name. These are two people that have greatly inspired parts of my career, specifically IETF development. Um, and if you look at their resumes, it is crazy. It's tens of RFCs, millions of lines of code. They developed interesting technologies such as GRE, multicast, Lisp, RPSL. This is still stuff that we use today in our networks, even though we're like 20, 30 years later. So what I hope to talk about today is how did things like multicast develop? What challenges existed at the time? How were the social or political dynamics? Was it fun to do, or was it a terrible project? So give it up for Dave and Dino. Thank you for joining me. So Dave, Dino, how did the two of you meet? It was not on Tinder or any of the modern day apps. It happened in a different way, I think.
Yeah, it was even
Should I
before
start?
Orchid. There was no
Yeah,
social media whatsoever. There was physical social
Dino,
contact. Go ahead, Dave.
I have some bad news. It was before the web,
Yes, this is true.
quite a while. Yeah.
You wrote each
Yeah.
other letters?
Well,
No, we used
there was only
FTP.
three applications, FTP, SMTP, and Telnet. Just what the previous talkers said not to use, right?
No, but let me see if I can answer Job's question quickly a little bit. I was working as a network engineer at the University of Oregon. I got lucky and got involved. I'll just say this. Oh, first off, Job, thank you very much for having us and for your questions. It's quite a bit of fun. So thank you for that. Um, I was I was lucky enough to get involved in this project in building statewide networking in Oregon, and it was during the ATM era. So it was an ATM network, and we did it in conjunction with US West. And what they wanted to do, being a LEC and all of that, they wanted to do the typical thing that telcos wanted to do with video and audio, which was run them over these highly QoS conditioned, essentially PVCs. And we didn't want to do that. We wanted to run things over IP. And at this time, the M-bone was just becoming sort of a more something that the normal human could get at, right? And so we started building a lot of multicast infrastructure over the top of this ATM thing. We're just using the ATM as circuits. And so then I started going to the IETF, and one thing led to another, and I met Dino, and we did tons and tons of crazy things on crazy multicast things. This was in
So what was the
circa
first meeting like?
this would have been circa 1990 or 91 or something.
Right.
To think I was
I
five.
think
Probably
we.
before you were born.
So, as Dave said, he was at University of Oregon. I was at Cisco writing code for iOS, and it was before I did data center stuff, which was later in my career at Cisco. But basically, Dave was, I wouldn't even say a beta site. He was really very early on taking images that were really just coming from engineers and testing it. And since he was so flexible in his attitude and willing to try things, and boy, I made him go through some crazy things. But in those days, the internet was a sandbox, and we were able to really, experiment quite a bit, try crazy things. And yes, we would GDB and breakpoint core routers in the middle of University of Oregon's network. I don't know how he was able to get packets to get around the points we were testing, but he did a lot of magic configuration stuff. But it was just, I mean, it sounds like the wild, wild west, but it was so fun. It was incredible the amount of learning we did in a short period of time. And, we didn't have chat groups. And I mean, it was, Dave, I think it was even before AOL Instant Messenger that we had these things. I think we were going back and forth
It
with
was.
email. That was the
It
only
was.
form. We didn't really do voice because we had, and let's see, did we have a screen scraping capability where you could, oh, I think he just copy and pasted text into email, and that was the debug output, right? And we only had ftp.cisco.com, which is where I would put images and where he would pull them. So, I mean, people kind of work the same way now, but they use more modernized tools, which are way more efficient. But it really took effort by human beings to make this stuff work. Go ahead, Dave. You might want to add to that experience.
Yeah. So all of that, and a lot more. But I'll just tell you, just as an anecdote, the first time I ever went to Cisco, I was this. I think I was in building wherever the EBC was. Maybe it was building 10, but I think it was before the numbered buildings, right? So wherever the
Building
EBC
D, I
was,
think it was. Yeah, right.
yeah, maybe building D. And so I walk in there, and this guy, this sales guy, who wasn't our salesperson, was the this guy, this Merrill McAdams guy, who's just a legend at Cisco. But I walk in there, and there's this sales guy called Martin McNeilis, and I think he's at Arista right now. But he says to me, "Oh, aren't you that guy from Oregon?" And I go, "Oh yeah, yeah, I work with Dino." And he goes, "Yeah, I want you to work with us because, as far as I can tell, you guys will run any damn thing." And it was really, he was talking about, yeah, Martin McNeilis,
Okay, let's spill it.
any
What
damn
was the
thing.
worst thing you ever ran that Dino created?
Oh my God.
Where
Worst
do we
isn't
start?
yeah, worst isn't exactly the dimension. It's like how I think a better kind of kind of metric would be something like, how long did it take me to recover from loading that code on one of my routers? And
You
sometimes
know,
it took a while.
it was one of the way the exchange worked, Job, was like, I can't figure out this problem, Dave. I have to give you some debug code, and it's going to crash. I'm warning you, and it's going to crash this way. And then Dave would load it, and he says, it didn't crash that way. It crashed some other way. And then we said, oh shit, what are we going to do now? And so I had to give him another image so it could crash the way I was expecting it to get the data that I was expecting. And that would go back and forth for all morning or whatever. But we did learn things, and we were able to get there. Now, was it efficient? No, but it was the only tools we had at the time. And these were the days where I thought that, wow, we could build images and we could learn things really quickly. To us, that was fast. And now when you look back, you look 30 years later, it's just like, I can't believe we had the patience to do all that. And this was me coming off of working on CDC computers where I was working in assembly language. So just the fact that I could write code in C and actually give somebody an image rather than wake up in the middle of the night and have to load something and get dedicated time on the machine. This internet thing was so cool because somebody could run new software. We were on the same time zone. That was huge. Being on the same time zone was huge. But the fact that I could compile something, somebody else, somewhere else could pick it up and put it in a network, that was like way cool and super state of the art, right? Everything's relative.
And these
There's another
were
part of it
images?
too. Yeah,
These
yeah,
were images
images.
that were
Yeah.
like 20, 25 megabytes, so you were hauling them around
Oh,
over
bigger,
Yeah,
50.
right.
bigger,
Well, don't forget,
bigger.
it had all these things, all these protocols like Novell and Apple Talk and Banyan Vines. I bet you most of the people on this call doesn't even know what Banyan Vines is, right? So these were, the cool thing about Cisco was it was truly a multi-protocol router, which means, we had 6 implementations of a variation of RIP, the routing protocol, right? And we had 6 variations of trying to do the data plane at different levels, right, on the line card. Autonomous switching was microcode on the line card, and all these different levels. So we kind of like implemented the same things over and over again. And then eventually the industry made Cisco engineering more efficient because everybody could then start working on IP because IP clearly won, right? So so yeah, they were large because everything was static and non-linkable. But I don't know, Dave, how when I gave you a typical image, I mean, what were the link speeds at that time at Oregon where you could download stuff. I would say minutes you would get something, right? Not seconds, right?
Yeah, yeah, minutes.
Minutes,
But
yeah,
Job,
yeah.
we had a 56K, two hops to the NSFNet regional in Seattle, two
Right.
56K hops. Um, anyway, one thing I wanted to mention, Job, is and you guys, well, I'm not sure exactly, but I think a lot of you guys missed this, but there used to be something at the IETF and at NANOG and at RIPE called the terminal room. And in the
Oh yeah.
terminal, because there was no wireless, This is predates wireless. And so what we would
There's no
do
terminals
by
nowadays.
yeah, well, this
Yeah,
predates wireless by a
right.
couple of decades, literally a couple of decades. By the way, we could tell a story too. The first time Dino ever saw wireless, I had one of the Steven Stewart deck roamabouts, and we were in a working group. I forget which one it was. I was sitting next to you, and I said, "Hey, Dino, look at this," because I had a wireless connection, and nobody else did. Steven Stewart went around and put these things in and all this stuff, and Dino said something like, "Wow, this makes the IETF useful finally. It actually work while I'm here." Anyway, I wanted to,
We were able to do debugging from the lobby rather than the terminal room, right? So
but what I yeah, but what I wanted to mention is this terminal room was a whole social event, and what would happen is um, all of our ISP friends, and it was just the who's who of the era, right? And we'd all go in the terminal room after the whatever we're at the bar or whatever, and Dino would fix bugs late into the night for everyone who was in there, and there was this camaraderie around this that I don't know if that exists anymore because I'm not really like kind of in the groove of that or anything, but there was it was a social event in the terminal room where we all worked on problems that we had or designs that we were interested in. And, like I'd have code, hey, this doesn't work. And then I had to prove to Dino that it didn't work, but then he'd just fix it or make the feature, while we were there. And so, that was one of the big losses that came with wireless. And when I spent a lot of time working in NANOG, I tried to figure out how to recreate that, that whole scenario that was there, but it never really happened because I think that was like one of the most productive, periods of time where we'd get in there and we'd all just, do it.
I think nowadays in IETF context, some of this activity happens at the hackathons. It's the 2 or 3 days
Oh yeah.
before the official IETF meeting, and its purpose is to facilitate interoperability and yeah, make it kind of a social thing. Get different vendors, different implementers at the same table, and be like, well, why is your software not reacting this way to this packet?
I don't
so
remember
I
if there were other implementers besides Dino in that scenario because what I do remember okay, so it predates Juniper. So who would have been the other
yeah,
router
right.
vendor? I'm not really sure. But
Mbone,
most of the people who were
Gate D.
yeah, maybe
Gate D
Gate
was
D,
the other
but I
router
don't
vendor. Yeah.
yeah. And but most of the people in there were the ISPs from the large national backbones because a lot of times we're working on multicast, not because I think Dino and I both. I mean, it was cool, like he said, and it was fun. But the ISPs, I mean, you can see the attraction of it. If I could just at that time, you know, bandwidth was really expensive. So the attraction of it was, oh, I can send one packet down this link. Hey, that and exploded on the other end. Hey, that's a fantastic thing, and everybody wanted that, right? And because people were afraid of, I don't know if afraid, that might be too strong a word, but people were concerned about having multiple video streams going down one pipe like we have today. Like with application layer multicast.
But
And
it was
people were
very,
very concerned about it.
Dave, it was very
Go ahead.
much like things are today about peering, right? People only wanted one stream coming through their network, but somebody had to replicate the packets. So the different ISPs at the peering would say, just give me one packet, and I'll decide if I replicate many times. They would just send one stream through their autonomous system and want to push replication to somebody else because the replication cost then was multiplying packets on their network. So, take the good and the bad or whatever. One comment I wanted to make about the hackathon versus what we did is the hackathon at IETF is really cool because it's people that are taking fresh ideas from newly written internet drafts and trying to write open source code. They are trying to do it for interoperability, but it's usually one implementation that everybody uses. In the older days, we had stuff called public domain code, and it was a reference implementation that people would take to build their own implementation and then market it and change feature, enhance it, and bug fix it a different way. So those two terminal room sessions, we were actually debugging code that was actually going into the production routers. It wasn't like a prototype or experimentation in trying to get things. So I think the hackathon is earlier in the development process where we had ideas and the RFCs were a little bit more established, and we were actually trying to get the code running in production because we needed more fundamental things to work earlier. So, but the great thing about the social aspect of the terminal room is like, oh, wow, while we're learning about these problems, there's these really cool features we could do. So let's get this operator, let's get this researcher, let's get this vendor together and co-offer an RFC. And those terminal rooms would produce ideas where the next terminal room at the next IETF, we would have implemented it. And we turned it around quickly. That was the key, is that, every 3 months we did last IETF's RFC or idea. That was what was really nice.
I got a question that may be hard to answer. What is the one RFC or internet draft you regret having written most?
MPLS. Sorry.
You mean
that
the
was
label
easy.
stacking?
But I know what you're getting at. Go ahead, Dave.
None. I mean, some of the, I mean, what I would always say about my writing in the IETF is, I prove that anybody can publish any kind of crap in the IETF. I prove that. But I mean, it's like in those days, it was more about, the network wasn't such a refined thing as it is now. It was more for me. I'll speak about me. I just wanted to work with all these people. I didn't care what it was they were doing. It's like you get around somebody like Van Jacobson, John Crowcroft, Leisha, all these people, you just want to work with them, because you can learn so much just being around those people. And it was such a, like I think I told you yesterday, it was such a fortunate thing to be in that time and place where you could interact with people like Dino, Van Jacobson. It was just a fantastic experience. And so a lot of that stuff I worked on. I even worked on DNS for a while because I wanted to work with some of the DNS. Yeah, I did. Yeah, because I wanted to work with some of the DNS people and learn what they knew, which was substantial, I mean, about this. So, I mean, as far as, if I had to say what was the hardest one I ever wrote, maybe it's got to be MSDP, because I could never figure out how Dino's code worked. So I could never write what the algorithm was for pure RPF in MSDP. I just couldn't write it. I tried so many times. And I finally recruited Bill Fenner to try to help me.
Because the code was changing weekly.
Yeah. And I finally recruited Bill Fenner to try to help me. And between the two of us, we still couldn't do it. So the end of the MSDP story really never had a solid spec. And I'll just tell you, just to go way to the beginning of it, for people who don't know, probably everyone, there was an epic meeting at Cisco involving John Myler, Yakov Richter, Peter Lothberg, Dino, and me. And we were trying to, I think there might have been somebody else there, but maybe that was the whole group, right? And what we were trying to do is figure out how to do multicast peering. And we had tried so many different things, and like dense mode exchanges and all these kind of different things. And Peter Lothberg, what he said was, well, why can't we just have the RP tell everyone else where all the sources are? And that's the entire design spec for MSDP right there.
Yep.
One sentence.
So Job, I'll answer your question the opposite way. What do I think is one of the most foundational RFCs that either one of us wrote? And I have to date it back a little bit later after we did the multicast stuff. Was Amsterdam, October 2006, Amsterdam routing workshop. It was an IB workshop on routing and how to save the internet and reduce the size of the routing tables. It was Dave's RFC that basically documented what went on and defined all the problems super clearly. And that was the basis for me and Dave and Vince Fuller and Daryl to build Lisp, because we wanted to solve the routing table problem. And it turns out by building a level of indirection, we solved all these other use cases that we didn't know about or didn't think would be popular now, 14, 15 years later. So I thought that was a great RFC, Dave. And the thing was, since it was such an important problem, the IAB shot it through to RFC so quickly. That thing probably made it to RFC in less than 3 months. That's kind of unheard of, right?
Mm-hmm.
Hey, Joe,
These days.
just as an aside on what Dino just said, and I want to just come back to the great fortune that we've all had being associated with the internet. When I was first starting out, we had this 56K to, it went to Corvallis where Oregon State is, and then Oregon State had a 56K to Seattle where NorthwestNet, which was our NSFNet regional, was, right? Well, the routers that were used in that network came from the NSFNet regional because of the way granting and this stuff worked, right? They had Proteons. We had Cisco. Oh, so Proteon might have been a competitor, Dino. Anyway, so we had Proteons,
Oh, yeah.
and
That's
when the Proteon booted, it did a lot. I mean, it did a lot of stuff. But one of the things it did when it booted is it said TCP/IP software copyright Noel Chiappa. So who's Noel Chiappa? I'm thinking to myself, and 20 years later, we're working on Lisp. And Noel comes into the little group, and I get this fantastic experience of being able to work with Noel, who's kind of an internet genius kind of guy, right? And it was fantastic just having him in there and getting his insight and all of this stuff. And if you like Lotus cars, he knows everything. He had like 20 Lotuses or something, but it was one of these situations where. It was one of these situations where just fantastic luck to come into contact with these people.
So Noel was one of those guys, we can call him a transparency guy, where he would write in real time on transparencies on overhead projectors. We talked about that a little bit yesterday, where these, Van would just get up and write code. He would create an algorithm and write C code on a transparency without smudging it up because there was no typos or anything like that. So
That's
Noel was
crazy.
in those class of characters where, as part of the IPv6, looking at all the possible protocols that could have been the next gen. We called it IPNG at that time, and IPv6 was the one that actually was selected. It was actually called SIP, or Simple IP, which was an 8-byte address turned into 16 bytes, and that's what we know as IPv6 today. But one of the proposals was by Noel, and it was called Nimrod, and it was a very advanced way of thinking about how to do the internet. This guy could probably implement or design an internet using, a half a dozen different architectures and tell you the pros and cons of each one. And he was pretty emotional and passionate about during those days because he knew what could work and what needed to happen. And unfortunately, a lot of his ideas we could use today. However, the IB, the internet, the IETF, the IRTF wanted to take an incremental nature and just increase the size of addresses. And I know a lot of you guys probably will say, was it a good move? Was it a bad move? It's hard to say. It's been really hard to make IPv6 ubiquitous, even though it's better now than it has ever been. But could we were so worried about feature creep and second system syndrome that IPv6 was simply just an address size increase and really nothing different in functionality. And Noel just said we had to take a look at the routing architecture because the routing architecture is pretty much the same in IPv6 as IPv4. You push routes around with an IGP and a BGP type system. And so he was very instrumental in thinking that the internet needed a separation of addresses at these different layers. Because, we all, let's face it, and a lot of people, internet people, don't want to admit it, we did learn a lot of interesting concepts from the OSI reference model and how each layer had their own set of addressing because it was abstracting out. And so we knew that the TCP/IP suite didn't have that, and how we could fix that. But anyways, no, I mean, I'm glad you brought it up, Dave. He was definitely visionary and helped us in the early days of Lisp. And still, his name's on many of the RFCs that the working group's still working on.
Yeah, about larger address spaces, I am guilty of this as well. When large communities came along, there were competing proposals that allowed all kinds of features and flags and key value type things to be stuck in this wide community, and it would be, almost Turing complete. And I argued fiercely, it's like, no, we're in a hurry. We have 6 years to get this deployed in the wild. We need just larger space. That's it, nothing else. And in doing so, I also know that the next 20 years will be stuck with just a larger community that has none of the appealing features that could have existed, but
Right.
we ran out of time. And
Yep, that's good insight. So
in the
it's
moment
funny,
that it happens, you're like, what are we going to do? We have to ship specs. We need to keep this internet thing running.
One of the
Yep,
concerns,
exactly.
though, oh, go ahead, Dino. I'll wait.
I was just going to say, and we talked about this yesterday. Dave felt that we met because we kind of forgot how we met. Is that I was working on something called Tuba. A lot of us were working on something called Tuba. Tuba stands for TCP and UDP with bigger addresses. It was running the TCP/IP transport protocols and above the applications over CLNS, which was the network layer. And the reason I'm bringing this up is, we're during the IPNG days when we were on the director trying to figure out what to do, we wanted to use CLNS because the NSAP address was variable length. And variable length meant that the addresses could be smaller if you wanted them to be, or a maximum size of 20 bytes, right? And of course, we had, Dave, you probably remember this, but we had the router versus host wars, where the host vendors wanted fixed addresses in a certain place, and the router vendors wanted a variable length address as byte 0 of the network layer because we thought it would be easier to get memory into an ASIC based forwarder much quicker. And so basically what happened was, what won was we knew 64-bit processors would be the norm and would be around for a long time. And as we speak today, 20 years later, we still aren't at 128-bit processors, or, if we are, we could actually put an entire IPv6 address today in a single CPU register. But we're not sure if that's useful enough because a lot of people use 64-bit addresses, the lower order 64 bits of the IPv6 address for doing host-based stuff. But anyways, the point here is that we tried a lot of different options and used different protocols, and it turns out that it was really a 64-bit address that we wanted to run with, and for political reasons, let's double it just to be safe, and that's why we have 128 bits.
Yeah, I remember
Go ahead,
that.
Dave.
Dino, I remember that guy, Danny, somebody from Sun. He was the guy who was pushing for during the IPNG. I'll think of it.
Danny.
But Job,
Yeah, okay.
Yeah, I'll think of it. I just wanted to mention the one thing that that happened around the time we were trying to do the, what should we do about the, it doesn't seem like people care that much about routing table sizes anymore. But one of the things that people were really concerned about, okay, because in the Vince Fuller era or people like that who were very active in the IPNG thing, they were operators, but what they had was AGS pluses essentially. And so what does this mean? This means that the route processor has 16 megs. And, so every slot, and Tony Lee had a proposal, I think it was Tony Lee had a proposal, or maybe it was Sean Duran, one of these, or maybe both of them, had this proposal where they would charge for slots in the routing. So the ISP would just charge. If you're going to
that was
blast a
Sean.
lot of, yeah. Um, uh, and so there's a lot of stuff like that, but people were worried about, with IPv6, one of the big worries was not just the size of the routing table, but that it would be deaggregated in the same way that the IPv4 routing table was, but it would be worse. And this is why it would have been worse. I don't think this really developed or hasn't developed yet, but the way it would be worse is if you have a giant aggregate, that the fact that you aggregated it actually is an abstraction that hides all of the dynamic behavior of the network underneath it, inside
That's
the
right.
aggregate, right? And so now I have mobile IPv6 or whatever, and now I have all these 128s floating around everywhere, whatever they are, and or just longer prefixes, whatever whatever the subnet mask is. So they're just longer
Punching holes.
prefixes. Yeah, punching holes, yeah. But all of these prefixes expose the dynamic aspects of the network that wouldn't have otherwise been exposed. So now, not only did you have a problem with how many slots do I have, that's not a problem anymore, but in the AGS era it was. Not only was that a problem, but now the CPU was at risk because now the route processor had to deal with the dynamic nature of the network that wasn't exposed previously to that. So that was one of the things
Right,
that people
right.
were very, very concerned about.
Yeah, it turns out in terms of aggregation that a lot of organizations just want independence. And when it came to V4, they would keep adding more and more blocks, but they would retain one ASN. When it comes to V6, yeah, we see a little bit less deaggregation, but people still do it when there's independent sites. But if you look at the growth curves of V4 and V6, it actually seems very predictable. And the current hardware seems to be up to spec for, at least for the
Yeah,
forwarding plane.
yeah,
So when we thought
yeah.
about these punching holes and switching from one ISP to the other, that was actually mobility happening, but it was done statically. In other words, if you had two connections to different service providers, and either if it was a provider independent address or provider assigned address, you had to put a more specific into the other one. And what we said is that you had this address independence because if you switch providers, you wouldn't have to reassign the IP addresses at your site, and that's why we defined EIDs and locators. And it turns out that is mobility. That means you can actually move anywhere. But back then, it was moving a site to a new service provider. You physically weren't moving the addresses or moving the computers. Now, today's with VMs and containers, we see these systems popping up, and we want to identify them based on a service or something. And so now they're truly moving. And I mean, and of course with mobile phones, you feel the physical movement rather than a container has IP address 1111 somewhere and then it pops up somewhere else as 1111. That's a mobility event, but that's still very much like multi-homing. But when you have a phone that's moving around, that's multi-homed with multiple radios, then you really see this physical movement happening. And that's what the sort of things we use lists for today is real mobility, right? With shortest paths.
But
That's the key is that I have this presentation that's really cool. It's called Subnet Suck, and that we never need VLANs, and that where you are is just some detail like Ethernet is. Nobody really cares what an Ethernet address is. It just knows that you pop up. So having who you are is what's important. If you could define this service, this is why you want to have these sort of static EIDs around. Anyways, I don't want
But
to
what
make
by
this
the
a
happened?
way,
less commercial.
by
Yeah.
the way,
What
by
happened
the
to the
way,
dream, though? You first, Dave.
What?
I just wanted to mention that this problem of punching holes and mobility, Noel actually solved this. This was solved in Nimrod.
Nimrod, yeah.
And this was one of the things, this was one of the features that really set a lot of people off and made it so emotional that this particular problem wasn't solved. And Noel actually had solved it, and in a well documented way. I think there's actually even a textbook on Nimrod somewhere. So it was well documented, and he solved it in a very elegant way. But like Dino said, it wasn't incremental.
Yeah, and nowadays we have clouds that were built by people that grew up in the IPv4 shortage, and we can now see massive layers of NAT in every virtual machine deployment of scale. It's so crazy that an inferior technology keeps being pervasive in
Well,
real world technology.
I'm glad you brought that up, Joe, because Um, this is a really good story. Going back to all the work Dave and I have done together. In the early days, we were out in front, the protocol designers, meaning we would design something, and it was the NAT vendors that said, oh, this new protocol came about. We have to punch a hole or deal with it in a NAT device. It's now turned itself completely opposite, where now when I want to build a new protocol, I have to make sure it can get through a NAT. So now I have to put NAT traversal machinery into my architecture to deal with the single or double, triple NATs, as you're saying. It's really changed. And it's a dominance of deployment sort of thing, and how people kind of shuffle back and forth. And it says, no, you have to adhere to my architecture. No, you're building a new architecture that's brand new. You have to adhere to what's already out there. And I think the internet designers were much different than the OSI designers, because a lot we were practical. We had to get working with what was there, and trying to deploy Lisp on a network that already existed made us have to make really hard decisions. And people would argue they were non-elegant decisions, but we wanted incremental deployability. And how do you do that? How do you change the tires on the car while it's still running? That sort of thing.
You run really, really fast while you hold up the car.
Yes,
Oh,
yes.
oh yeah. Yeah.
So,
I wrote
given
a I
that
wrote
we
a
are,
presentation. One thing, I just wrote a presentation um, for NaNOG once around the time when all this was happening, and it was carrier grade NAT, and I forgot what the scheme was that took some of the it took some of the bits from the port ID, and you know did all these crazy things, right? And I think that I'll have to go find it, but I think what I called it was it's the end of the world as we know it. And on the cover of it, I
Yeah.
had like Chicken Little watching the sky falling and all this stuff. But somehow it didn't happen. You know, the sky did not fall. The internet's still here. It's still working. It's still growing. Somehow it has this resilience. And, I mean, that was one of the things I
Well,
wanted to study with my friends at Caltech was where did this resilience really come from at some more fundamental level than just, um, the the protocol design or something like that. But I never did that work. I was too lazy.
I mean, Dave, you bring up a good point, and maybe we should be intellectually honest and say if it wasn't for NAT, the internet wouldn't be as big as it is today. We really have to say that. But and we were able to grow it, and we were able to use it in some weird ways that nobody predicted. But now I'm starting to think of the 5 ESS sort of situation where AT&T built a phone switch a long, long time ago, hundreds of years ago, and it was pretty simple and it was managed by people, and then it grew into something that was completely unmanageable. I think Job and the current generation of engineers would say this network, yes, it works. It's kind of amazing how it was all put together, but the cost of managing it is just incredible. And we need to take a look at it all over again. And I don't know, hopefully IPv6 can be something that we say it will, IPv6 by definition, no NAT, no MSDP, right? These are important, attributes of this new architecture. So,
Job, you, you,
but
you
even
probably
with
missed this.
IPv6, it took years before in the RIPE community you could get IPv6 space if you were single homed. So people would either ignore IPv6 entirely or use ULA space and net their provider managed space into their internal
got it.
space to avoid having to deal with a renumber in 100 separate places and just in a few edge
Yep,
places.
yep,
So I know the
yep, yep.
IPv6, some in the IPv6 crowd argued against net, and but it didn't happen. net won.
But it
Yeah,
also only,
again, yes.
that scenario that you described works right up until there's mergers and acquisitions. And then it's like you had 1918 space and everything's screwed up, you know? It's like,
Yeah. Luckily, the
And that's
policies
how
were
that's how the cloud
were
networks
changed.
run. It's all with 1918 space, right? So,
yeah.
in fact, NAT is a perfect locator ID separation protocol, right? Because the EID is 1918 space, and the RLOCs are basically global addresses that are in BGP, right? We know that. We knew it all the time, right? So,
I wrote this one RFC about complexity when I was working really, like when I was at Sprint in the really early days of that, probably around 2000 or something like that. And in that has a whole thing about how what NAT is really doing at some fundamental level, and why, the question I had was, uh, the question I had was, okay, we're in the internet space. The internet operators, or I don't know what to call them, so I'm going to say this. I don't mean this in a derogatory way, but sort of the purist. No NAT, right? We can't have NAT. That's impossible. End to end. That's it, right? And, it's sort of democratizing, and there's all kinds of reasons why. But it turns out that NAT does this really interesting thing, and that Dino was kind of alluding to it, of coupling this process of coupling the sort of the inner addresses to the outer addresses, and that coupling, that process of doing that is what causes the management headaches that Dino is talking about. You just have to back it out a ways, but you find it if you do it.
so
Yeah.
And
I
then
have a proposal.
you can have carrier grade NAT and make it 100 times worse too, if you like.
So for all the young engineers that are listening now, and I like to get Job's and Dave's opinion about this, is when we started, we all had mail servers and DNS servers, and it really felt like a peer-to-peer network, and that not all our packets were going to these monopolies and stuff. There's this blockchain talks about this decentralization, and how everybody could run the network together and we could be one happy family. We did that in the early days of the internet. Decentralization was there by default, and we've evolved where it's not that way anymore. It would be nice if we can get back to that point where there's more independence and freedom, democratization, decentralization. Dave, do you have an opinion about that? And Job, I'd like to hear what the current generation of the internet is doing, or do they even care about that?
So I'll go first, Job, and then
Dave?
you go, okay? So just to put a little bit more color on that, what we did was everybody had a T1, everybody had a router in their own house, everybody had their own address space, and everybody had an AS. And T1 would go to different places. Fortunately for me, I had built a sort of a local internet exchange at the University of Oregon, so I just slapped a router on that thing and then made a little ISP for all my neighbors. Or well, it was for Lucy, Hans, and Joel, if you know those guys, those people. But in those days, we built like little ISPs, and they were at your house in order to do this, a lot of this debugging and development. And in the early days, of course, we did it on, like Dino and I did it on the U of O network. But later on, we had T1s, and we were, in those days, having a T1 was like state of the art, And there's still a 25 pair cable tacked to the side of my house that US West put there that's, completely dead. But there's a Westel in my basement and stuff like
That's
that.
museum material. You better keep it there.
Yeah, how do we get back to decentralization? If we look at resources available to younger engineers these days, you can get the ASNs for basically free. IPv6 space costs $50 a year. You can set up peering fairly cheaply, depending on your exact geographical region. But I think where a lot of eyes need to focus right now is the centralization that exists or manifested itself in the 5 RERs taking on RPKI cryptographic functions. And I think for decades, the RERs have done a wonderful job of avoiding assigning duplicate ISP space to different entities. I think globally unique space is an important quality of the internet. But then how do we safeguard that? And as a naive solution to this is a single source of truth, which is then hidden in a PKI. But is that robust? Is it robust enough for the years to come? Are we going to see a model where multiple cryptographic entities start co-signing things, and then that you get weight levels of? I don't know. We're in the very early days of this technology, and I think the technology itself is not inherently centralized. There's a lot of flexibility in how it can be distributed.
So, so Job, you just said how you could do it with today's tools. Maybe the first question to ask is, do you want it? Do you have a desire to be decentralized? And the reason I'm asking that is because when I work on stuff now, people care about privacy in so many ways, but it's usually the 40 to 70-year-olds that want to do it. And like the Gen Zers that are coming up in a society where they have no personal privacy and they don't care about it because that's all they know, and they're not asking for it. So I'm wondering, building the internet in a general way, not just at the router level that you talked about, is decentralization desired at all? Is the internet okay the way it is in terms of services and things?
We got to ask younger people. It's not us. All right.
Right, right.
I'm being signaled from the production room that we have overrun with a few minutes. I want to offer you both 2 sentences to say hi to the crowd, and then we're gonna end this conversation. Dave, you go first.
2 sentences, huh? Well, I
Any
guess
topic.
the first one is, okay, the first one is thank you guys very much for having us, all of you. It's been great being here, and thank you, Job, for arranging this. And also, thank you, Dino, for doing it. It's been great talking with you. I haven't talked with Dino in a little bit, so thank you.
Yeah, I think this meeting is going to help us get together more. So thank you, NLNOG, for reacquainting Dave and I again. That's great. And yeah, I'd like to echo the same comments as thanks everybody for listening. And we are resources. I still do a lot of work, and we're here, and we have a lot of experience to share. So you guys could just send me an email. I'm available. You don't have to go to some
Yeah.
second tier website. Farinacci@gmail.com. Send me an email if you want a question answered or you need help. We're here to help, and we want to make your jobs easier. We want to tell you to make new mistakes rather than the mistakes we made, right? So we're
What are
available. At
the
least I'm
chances?
available.
Oh, yeah,
All
me
right.
too. Now,
I'm gonna make
if
sure
anybody
we
has
just
the
put
courage,
your. I'm gonna make sure we put your email addresses on the website. And thank you for
okay,
this
that's
offer,
great. Thank
because I mean, I literally myself rolled into IETF by emailing you guys and being very surprised I got a response back from these highly respected individuals on the other side of the planet. So yeah, awesome.
We're all
Gentlemen,
engineers, right? We're trying to solve problems.
thank you so much for your time. This was fun.